Today we're going to go through lots of topics related to meta learning, and in general, I'm gonna split this lecture into two parts. The first part is going to be broadly introduction to meta learning. I'm going to go through some motivation and a bunch of examples. We're going to look at the generic formulation, of course, probabilistic view to make it connected to PGM. It's pretty connected and it's pretty related. And two classes of methods, basically gradient-based meta learning and embedding or prototype-based meta learning. In the second part, I'm going to focus on meta-RL. So that's going to be somehow connected to the lecture that are already given previously on reinforcement learning as inference. What this lecture is not covering, and meta learning is a fastly growing field, and there are different subfields in some areas in this field. So one part that is not covered, and it turned out to be too much of the material to cover in one lecture, is AutoML, which means automatic machine learning, which is also regarded as meta learning in some sense, but it's slightly different from what we're going to be talking about today. So if you already know meta learning or your research is about meta learning, probably you will not learn that much. This is an introduction, first of all, and maybe you will sort of learn some interesting points or implications that we're going to go through. But generally, our goal is to give you an introduction and give you a good starting point to start reading papers in this field. Okay. All right. So let's get started then with the first part of Intro to Meta Learning. So I'd like to start with this quote that you see on the slide from a paper by Rich Sutton, Anna Koop, and David Silver, back from their paper 2007, where they say that much of machine learning can be characterized as a search for a solution that, once found, no longer needs to be changed. All right, so what they're talking about is the standard setup in machine learning, where we have a data set and we learn some algorithm, then we extract a model, and then we're sort of satisfied as long as the model's performance on a test set is good enough, right? So then they say that machine learning has been more concerned with the results of learning, or this model that we extract from the data, than the ongoing process of learning. All right, oftentimes this works. And recently with deep learning, this approach, machine learning approach, has started working really well. But the question I'd like to ask, does it work always? In which cases we actually need to be concerned about the process of learning rather than the model that we extract from a single data set. Right, so when is standard machine learning not enough? Right, we know that standard ML already had a lot of success stories, and I'm just showing here ImageNet, very large-scale data set that literally sort of kickstarted this revolution in computer vision. And we see a lot of creative applications that all reuse architectures that were originally developed on ImageNet, as well as the success story of solving the game of Go, right? And in both cases, we have a pretty well-defined task, either defined by the data set or defined by the environment. And in a sense, it is stationary. So the images in the ImageNet are not changing, the conditions are not changing. So once we've got a model that is performing well on a subset of the data from ImageNet, we have a confidence that it will perform sort of well on the test set. Similarly, with the game of Go, the game of Go is stationary in a sense that the rules are not changing, and once you master the game, you can keep performing and playing the game at this super grandmaster level, right? But how about a complex dynamic world? In a complex dynamic world, one of the applications that we can think of that involves complex dynamics is self-driving, right? So this problem, I don't know if you remember, in 2015, we all heard that some companies promised us to solve self-driving by 2020, and right now we know that it's a much more challenging problem than we originally thought it is. And the challenge comes from this complexity that is out there in the dynamic world, so that you can characterize as a very long tail distribution, where certain situations are never encountered in the training setting. You still want to be able to have some sort of guarantee that in the worst case you will not do something crazy, right? Or you can characterize it as a world that is changing, and maybe at a given instant of time you are in this kind of in one distribution, and another instance of time you're going to be slightly different distribution, etc. So this non-stationarity comes into the picture, right? Another application of interest could be heterogeneous data that we collect from people, right? A lot of these IoT devices, they collect a lot of data from us. And the question that we can ask here is, how do we use this data to build applications that are ultimately personalized, right? A recommender system that is specific to a given user, or let's say a personal assistant that actually fulfills the needs of a given user. And for different users, even though the inputs could be the same, the targets or the models that would like to serve these users often are different. And finally, how about the interactive robotic systems, right? We would like to build robots that can sense their environments and accomplish a lot of tasks and ideally collaborate with people. All of this is kind of far-reach goals, and this is where the frontier of machine learning research right now is trying to push. So meta-learning is not trying to solve this task, but I would say is a step towards trying to reason about them and approach some of the kind of simplified versions of these very complex tasks. Okay, so what is meta-learning? So let's start a bit more formally and look at how can we define for standard learning and how can we define meta-learning, how do these two entities relate. So in standard learning, we can say that we have a distribution over examples, and these could be input-output pairs. It could be just samples from a distribution, or it could be trajectories from an environment, right? And our goal is to learn a function that minimizes a certain loss and expectation over the distribution over these examples from this task, right? So our goal is to learn a single function. Sometimes we learn posterior distribution over functions, but we're concerned with a single entity. Now, in learning to learn, or meta-learning, we formulate the problem slightly differently. Okay, kind of go one level up. So instead of a single function, now we have a distribution over functions. And then each kind of distribution, each task, distribution over task, and then each task is itself a distribution over examples, right? And now we'd like to output an adaptation rule that can be used to test, that can be used at test time and applied to a new task and output as a function that is able to solve this new task. So more formally, again, we can write it down as an optimization problem, right? And in this case, we have this distribution over tasks or data sets, which is this outer distribution. We compute the expectation of some loss, and we'd like to find optimal parameters for this G function, okay? Now, this loss itself is an expectation, but now with respect to within the task distribution over samples, right? And then this expectation is taken of the loss of some function with parameters phi. And the important part here is that instead of trying to learn for every task a separate function, which is impossible because if we have a distribution over tasks, technically we have an infinite number of tasks, so we need to learn an infinite number of functions, right? We would like to learn this G function that would output us the F function, right? So basically the G function will generate the F function, and would like to make sure that every time the G function generates the F function, the loss is minimized, and the loss is minimized across an expectation across all the tasks. And I'm going to call, just for the sake of this lecture, this G function the adaptation rule. It can have different forms. We're going to look at different forms, and the argument of this G function is the task description. Right, in task description, again, it can be different forms. In some kind of approaches, people look at a few samples as the task description, which we're going to do next. But sometimes it could be something more rich. So it could be a natural language description or something else. So let's look at a toy example, which is a few-shot classification problem. So imagine that we're given a task where there are three classes. So say a ball, a lion, and piano. Right, and we have a training set, a small training set, and a small test set, right? Now, the case where we have a lot of tasks now will basically translate to having a lot of these small data sets, right? We have just a few examples, let's say one example per class for each of the classes, and we'll have a bunch of testing examples also coming from these classes. And our goal, in this case, to be able to take as input this training examples and produce a function that actually works well on the test examples. And we would like to have performance that is really good across all the tasks, let's say on average. So again, our task distribution or data set distribution is this green line, right? So this is distribution over data sets. Again, the adaptation rule can have different forms. The task description here is these few samples, few training samples that we're going to use in order to produce a function that works well on the test set, right? And finally, within the task distribution is basically every row on this illustration. Okay. So this is the notation that we're going to use throughout the lecture. Yeah, just are there any questions? Feel free to ask either on the chat or just raise your hand. Okay, so let's move on. So there are a lot of papers that actually study the setup, right? The original paper that proposed the specific data set was proposed around 2016, 2017. But the actual setup, this bi-level optimization setup, was actually considered back or proposed back by Schmidt-Huber in the late 90s and also considered by Sami Bengio in 1990s. Right. So more recently, people started looking back and looking at all these methods and trying to adapt them in the context of deep learning, where we have much richer and larger data sets, and in this case, metadata sets of tasks, as well as much richer and larger models, right, such as deep neural networks. Okay, so let's look just at a few practical examples. Where does this few-shot learning comes from, right? It seems like an arbitrary toy task where we have a bunch of examples in the training set, and then we want to learn to classify. Why does this make sense? Well, in some settings, it actually maps nicely into the problem of interest. So for instance, in recommender systems, there is so-called cold start problem, where a new user comes in. We have just a little bit of data for that user, but would like to be able to make recommendations for this user on a pretty good level. This paper from where just given the user history, we try to learn a simple linear model that would be able to classify irrelevant to the user, given just a few observations of what user already liked. I believe they applied it to the Twitter feed. The other recommendations that you serve to the user, but that you don't want to pull all the data and sort of store it on the central server in the cloud. Instead, you would like to be able to do all the learning and as well as serving on device. So in this case, you'd like to learn these models that can adapt to users on their devices pretty quickly. And also, the data that you have per user is pretty small, so naturally it sets you in the few-shot learning regime. Okay, so just a couple more applications. One of them is low resource translation. You can pretty much transfer it into a similar setup instead of using transfer learning. Well, I guess to give you a little bit more background, usually in translation, you need a lot of data in order to learn a good translation model. So for instance, if you have English and Spanish languages, you have a lot of parallel data that you can use to learn a pretty good translation model. But for instance, for English and Romanian or English and Latvian, for these two languages, there aren't enough data, so you need to do some sort of transfer learning or meta learning. So the paper that I listed on the slide, instead of using transfer learning methods, such as the left and the middle pictures, they propose to learn a model, use a meta learning method that I'm going to cover just in a bit, called MAML, in order to adapt translation from high resource languages to low resource languages. Finally, maybe one of the most impressive applications of few-shot learning is so-called few-shot video-to-video translation, where the task is to take an input video, a pretty short clip, and actually translate it into the target image. So instead of having a video of a person speaking, we'd like to have a video of Mona Lisa speaking, basically doing the same facial gestures. In the way that they do it, again, they have a large data set of these short clips for different people and different target images, and then they basically use the few-shot, they construct the few-shot objective, they optimize it, and they get this result. Okay. So just one more example that would be relevant to this lecture. Eventually, we're going to go into meta-RL, but the step between supervised learning and RL would be imitation learning. And actually, you can try to solve imitation learning with this few-shot few-shot approach and meta-learning. So how imitation learning works, technically have a data set. Usually you have a data set of demonstrations for a given task. So let's say the task is pick a block and place it somewhere else. You usually have a lot of demonstrations. You need a lot of demonstrations in order to learn a good policy that would be able to sort of replicate the demonstrated skill, right? But it's very inefficient because for every new demonstration or for every new task that you'd like to teach your robot, you need to collect a lot of demonstrations, right? So what this paper proposes is actually to restructure the problem such that instead of trying to learn a separate demonstration policy, a separate policy for each demonstrated task, we try to learn a meta algorithm that would output you a pre-initialized policy, and then given just one demonstration, you would be able to adapt the policy and sort of follow the demonstrations, sort of replicate the skill, the demonstrated skill. Okay, so all of these examples are again using this same general framework or general formulation of meta-learning. Maybe not necessarily this specific notation, but if you look at all of them, they all map into this formulation. Okay, so I just defined in this very simple few-shot few-shot classification example. I already defined what is the distribution over the data set, what is the distribution within the data set. I did not define what is the adaptation rule. So let's take a look at the first meta-learning algorithm, the first adaptation rule we'll try to look at. So the first one is going to be MAML, or model-agnostic meta-learning, which became pretty popular in recent years and was appeared at ICML 2017. Okay, so the intuition is very simple. Right, so let's say we have, let's say I give you these n tasks, and the first thing you could try to do is to train a model for task 1, and then test it on the test set. So get model, let's say F1. And then to solve task 2, you'll start again from a random initialization. You will apply SGD maybe on your model, right? And then you'll get sort of optimized model for task 2, etc. You can do this for all n tasks. But what if for every task we have only few data points? So the proposal is to start and optimize each model from a common initialization that we're going to call theta. Okay. Now, given a new task, when we start from theta, and then we just use the standard learning procedure or standard gradient descent. So we're going to go and define this G function, or the adaptation rule, right, as theta minus alpha gradient of the loss function of the task Ti. And the loss function is going to be computed on these training samples, right? So we can do that, and instead of theta, we're going to get phi. For every task, we're going to get a separate phi. Okay. Now, how do we select an initialization that actually works for all these tasks, right? Well, we're gonna compose all these tasks together, define the test loss, right? So we're going to define the loss, or use the standard cross entropy in this case, cross entropy loss on the test set, right? And we evaluate the function after we updated its parameters, right? So it's the function with the updated parameters evaluated on the test sets, and then we just simply average over the test sets that we have. And then we're going to optimize this objective function with respect to the initialization. Why? Because these new parameters are a function of theta, right? So everything here under the minimization is a function of theta, so we can simply apply gradient descent again. So it would be gradient descent around gradient descent. So this would require second order differentiation, etc. But you know, intuitively, what happens is that, let's say we start with some initialization, we compute all these gradients for different tasks. All these gradients are going to pull us towards the direction, intuitively again, towards the direction from which, towards the point from which we can reach each of the tasks that we have in the training set, right, within just a few gradient steps. Okay, so that's the intuition behind MAML. It's a pretty simple algorithm, and does it work? Right, that's the question that we can ask. Does it work? Well, on a couple of benchmark data sets, Mini ImageNet is the data set from which I just showed you the samples in this toy few-shot classification problem, and Omniglot is an even simpler data set. It's basically MNIST-like characters from 1,600 different alphabets. Right, and then they have two different protocols of how to evaluate these methods. One is called 5-way or 20-way classification, and then it could be 1-shot or 5-shot, which basically means, let's go back, way means is the number of classes in the problem, shots means the number of examples per class. Okay, so on the Omniglot, you can see that MAML performs really well. I guess the comparison that we should be looking at is the standard fine-tuning, right? Because other methods are just other meta-learning methods, but fine-tuning is really this kind of the most primitive baseline that you can come up with, right? So you pre-train a model on all the tasks, so you just try to fine-tune this model. And how good is this MAML learn initialization versus this fine-tuning learn or pre-training learn initialization? So it turns out it's pretty good. And so you can see more than 20% improvement in 1-shot setting, 5-way accuracy, and something similar in terms of 5-way accuracy, right? Okay, so we can actually also look at MAML, right, and this nested optimization problem from a probabilistic standpoint. Right, to do that, let's just introduce a little bit more notation, slightly redefined notation. So let's say we have endpoints that are coming from our distribution that corresponds to task TJ. For simplicity, we're going to ignore the labels for now. Let's say it's just distribution modeling task. And then we have testing points, the following points that are also coming from the distribution that corresponds to task TJ. Right, now the MAML loss that I just wrote you in a previous slide in this setting would look like this, right? It's 1 over j, which is the total number of tasks, sum over 1 over m, and then let's say we have m points per task, right? And in this case, m points are the m testing points, right? So we have m testing points, and then we're going to compute this outer loss, which is the negative log likelihood of the testing points from the testing sample from the same distribution. And then this is the inner loss. So basically, this is the adaptation rule. So we compute conditional distribution of these testing points from the testing set, given that the parameters phi j that are basically the adapted parameters, which is the initialization plus the gradient step, again, on the same loss, and then the gradient step is computed on the training points. Right, so again, we take the data set, we split it into parts. We first adapt parameters on the first part, right? And this is basically the illustration, right? We have distribution over tasks that produces the distribution over data. The distribution over data, we sample from this distribution, right? When we get to samples, we separate them. On one sample, we compute the loss and then adapt parameters of the model, and then we get adapted parameters, we evaluate them, and finally we get this final loss that is meta-optimized with respect to theta. Right, so this looks like a plate notation, so we can further a little bit generalize this inner loop that is very specific to MAML, and and more generally, think of it as just hierarchical Bayesian model, right? And in this case, in the outer loop, we have this random variable, or basically parameters, theta, right, that sort of imply or conditional on this theta. We can sample phi j, and this conditional step in MAML's case specifically, so basically this conditional distribution of probability of phi j given theta in MAML's case is a gradient step, right? More generally and more broadly, it could be arbitrary conditional distribution. Okay. So this is the reinterpretation, and it appeared as an iClear paper in 2018. So the authors further go and explore different ways to actually approximate this conditional distribution. And they show that meta-learning is basically the empirical base on this hierarchical Bayesian model, and you can have different approximation. MAML is one approximation. They came up with slightly different preconditioning, a slightly different approximation. I'm not going into the details of this paper, but you should look it up online. Okay, so let's. But before I switch the gears to the other type of meta-learning methods, let me know if there are any questions. No questions. Okay. Okay, so that was gradient-based meta-learning. Pretty simple. Start with initialization, compute the gradients on the subset, and then optimize the whole thing on the average of all the tasks. Now, is there another way we can solve this problem? Again, let's say we have these 3 classes, a bunch of instances, and then would like to do something with the training instances and then make predictions on the test instances. I guess like the simplest thing that one could come up with, right, would be the nearest neighbor classifier, right? So you can try to compare which instances are closer to each other and then make predictions based on the distance, on the smallest distance. And this is what another class of methods, I would say, tries to do. So in order to compute the distance, first of all, you need to define the representation on which you can compute the distance. Probably pixels is not the best representation for computing distances. So we probably would want to embed these images or these instances in some kind of embedding space. And then once you embedded them, right, we can determine sort of the class of the new instance by just looking at the distances, right? And then trying to pick the class with the minimal distance for that testing instance. So more broadly, if we have more points per class or more shots in the few-shot learning notation, right? In this case, we can aggregate these points and further construct the C1, C2, and C3, which we'll call prototypes of the classes. And once we have the prototypes of the classes that we constructed from the training small subset, right? Any test example can be classified using this distance to prototypes. More formally, how exactly we're going to do that? We can compute prototypes using an arbitrary embedding function. This could be, let's say, a neural net that takes in your images as inputs and outputs. You just, 100-dimensional vectors. You just average them together for each class separately, and then the predictive distribution is just the distribution given on this line. So it's Boltzmann distribution with the negative distance in the exponent, the negative distance between the corresponding class and the embedding of the testing point. Okay, now how are you going to train this? Again, you're going to have all the end tasks. For each task, you can compute this predictive distribution for the testing points, then compute the loss, and then average across all the tasks. So the only thing that you're learning in this case is basically the parameters of this embedding function. Okay, so it's an extremely simple method, and it turns out that it actually works pretty well. And even though this work was very much concurrent with MAML, so it appeared at NeurIPS 2017, as preprints, they appeared almost simultaneously on arXiv. And surprisingly, even though these matching networks and neural statistician methods, all of them use some sorts of adaptation rules that are sort of more complex. MAML used this gradient-based adaptation rule. Prototypical networks literally are use this embedding function and fully non-parametric approach, and they outperformed entirely all these previous methods, right? And they're super competitive both with MAML and on both of these benchmark datasets, Omnivore and Mini-ImageNet. Right, so these are 2 classes of methods, and one of the questions that arises by looking at these numbers and looking across many other papers that try to combine the 2 methods and come up with this, sort of hybrids of kind of learning fancy embeddings and then putting on top of that some sort of gradient-based adaptation of some of the parameters of the model. You realize that they don't go too far, or at least on these datasets, they're pretty close to these methods. Right now, these numbers are pretty outdated, so the best methods on these specific data sets get something around 80s or 90% in one-shot, five-shot, 5-way accuracy. But still, you can ask this question of whether, actually, how much of the adaptation matters, or the adaptation rule matters, versus how much the representations or these embeddings that eventually you learn from this multitask data set matter. And this is the question that one of the papers from iClair 2020 is actually asking. So they asked the question, is it rapid learning, actually, or is it feature reuse that MAML specifically is trying to do? And their study was focused specifically on model-agnostic model learning, this gradient-based approach. So what exactly do they do? Just to illustrate the question a little bit, once again, we have this MAML kind of structure where we have an initialization, and then we have this adaptation to different tasks. So in case of rapid learning, the diagram that they show pictorially, right, is that we find an initialization from which we can quickly, but still, quickly adapt to a new task. But the difference between the initialization in the initial parameters and the task-specific parameters is actually drastic, right? In case of the feature reuse, your adapted parameters are already sort of good enough or almost good enough, to solve all these tasks. And really, the bulk of the performance improvement comes from the feature that you're able to learn in this multitask setting. Okay, so this is the question that I try to ask, and to answer this question, whether it's adaptation or whether it's good representation, they conducted a lot of experiments with MAML and a version of MAML. So the version of MAML that they proposed is called ANIL, or almost no inner loop, right? So it's basically a MAML that was slightly edited. So in case of MAML, typically you have, for the function, you have a multi-layer neural network. And in this case, let's say you have a 3-layer neural network where theta 1, theta 2, and theta head correspond to the first 2 layers, and then the third layer is the head of the neural network that makes the prediction. Is there a question? Okay, so the head of the neural network makes the prediction. So basically it goes from this latent representation into the number of classes that you specified for the problem. In case of ANIL, what they proposed is to fix basically fix the theta 1 and theta 2 and never adapt these parameters, and only adapt the head parameters of the neural network, right? So the hypothesis is that if adaptation of the lower layers of the neural network matters, then probably ANIL should not work at all or should not work well. As it turns out, the two methods are almost identical, right? So what the authors discover is that there is literally no visible difference in performance between MAML and ANIL. They also looked a little bit at a variation where you train everything, with MAML, but then at test time, sorry, you don't adapt anything at all. So you basically learn a single model for everything, and maybe at test time you adapt a little bit the head, which is called the nil version of ANIL without the A, which performed a bit worse, but still the performance was literally within the ballpark of the MAML numbers. Right. So more details can be found in their paper. And the study not only looks at all these final performance numbers, but they also actually try to compare the representations in terms of how well the representations correlate in two different models across all the layers, across different tasks between the two different methods, and they find that there is literally no correlation. And even in MAML case, at the end, after the MAML is fully trained, after the adaptation step, the majority of the change is coming from the change in the head parameters, right? Because you basically need to figure out which classes to distinguish between, while the theta 1 and theta 2 and all the lower level parameters are literally not changing at all. Right, so it partly answers the question. It's still unclear. There are a lot of hybrid methods that sort of benefit from both gradient-based and prototype-based meta learning, but this paper sort of sheds a little bit more light on which component matters more. Okay. Now we looked at these two approaches, and previously, in previous lectures in PGM, I believe you guys covered Gaussian processes. So let's try to draw parallels with Gaussian processes as non-parametric models and this meta learning few-shot learning setup. Are these similar? If they are, what are the similarities? What are the differences? So my argument is that what meta learning is trying to do is it tries to learn a distribution over functions, which is some sort of a process, right? And we'll see what kind of process it is. So in few-shot learning, let's consider this regression example, just for the sake of example. Our goal is to really, by solving the task, we're trying to identify a function that basically generated the data, whether it is conditional probability distribution of classes given the inputs, or it could be just the target, right, y given the x in this one-dimensional case. And let's say we have these different functions so that the values of y are different for different x's. So given just a few samples, let's say from the blue curve, what you want to do, you want to figure out that actually the data is generated from the blue curve, not from the red, not from the orange or green. And by looking at this image, technically it is possible, right? So the goal of adaptation, right, of this adaptation rule is to, using this prior knowledge about the structure of this functional space that we believe is true, right? We would like to be able to identify these functions. So if you remember Gaussian processes, they are basically doing something very similar. So imagine that you have a Gaussian process and then you have a few observed points here, right? Given the observed points, or a few x and y pairs, you can compute the predicted mean and predicted variance as given on the slide, right? So basically you narrow down this distribution over all possible functions, sort of under the Gaussian process prior, to just a few functions that are kind of suitable with the observed evidence, right? And you can infer this posterior predictive distributions given the observations, and as well as given our prior knowledge that we actually incorporated or encapsulated in this kernel function, right? And in this case, the kernel function, so this Gaussian process on the right-hand side will probably not fit these sinusoidal functions on the left-hand side, because the kernel is squared exponential, so it doesn't have the right assumptions about the periodicity of these functions. But if we use some sort of periodic kernel, it's pretty much going to solve this problem, this meta-learning problem, very well. Given a few samples from any of these functions, my Gaussian process can nicely approximate the rest of the function. Right, so this observation was made by these authors, Garnell and others from DeepMind, and they proposed to sort of imitate what Gaussian processes do, but in a more kind of flexible way, so that we don't have to design kernels, because designing kernels could be pretty challenging. It requires, sort of understanding the space of the functions, and oftentimes it's a very ad hoc process. So maybe instead of designing the kernel, right, we can somehow learn it from the data. So on the left-hand side, you see that we have this, our standard setup, where we have some observations generated by different functions, right? And let's say we have some training observation, we have some target observations for which we don't have output y. So in the standard supervised learning, again, we distill a single function, and then we use this single function to predict all our outputs. So in case of Gaussian process, it's not a single function. Again, Gaussian process is a distribution over functions. So given arbitrary inputs, the predictive function will be different depending on what are the inputs we're going to have. All right, so they propose this conditional neural process architecture that sort of imitates what Gaussian process does, but is parametric, and it doesn't have an explicit kernel. So we have these observations that go through this H function, are transformed into these representations, R1, R2, R3. Then they have some sort of attention module that attends and aggregates, or basically aggregation function that aggregates these representations, and we get this R. Now, our G function, or G part of the model, will condition on this R and make predictions on the target points. Right, so if you think of this is basically how Gaussian process works. You condition on some variables, you infer the posterior predictive distribution, in this case approximated by G, and then you make these predictions from x4, x5, x6 to y4, y5, y6. So what they looked at, they looked, first of all, how well it, does it work comparably well to a Gaussian process. And on the right-hand side, you can see that they had some toy kind of examples where you have 5 context points or 50 context points or these training points, right? And they compare Gaussian process and CNP. And if you compare the two, they reasonably look pretty well. Maybe CNP is a little bit less regular, which is also good. It means that the CNP model can capture much kind of fine-grained structure, while Gaussian process is much smoother. But again, this is incorporated in the assumptions of the kernel function, right? But the cool example is on the left-hand side, where they actually applied it to images, which are extremely high-dimensional objects, right? And in this case, your x is actually a coordinate, right? So a coordinate along the axis. So it have x1 and x2 along the the width of the image and the height of the image, and as well as you will have x3, which will be along the channels of the image, right? And for each x, you can try to predict y, or the intensity of the pixel. Okay, so it becomes a regression problem in a sense, right? And then you can try to solve it with this CNP. So with the Gaussian process, or the standard Gaussian process, it's really hard to design a kernel that would represent natural images. It's virtually impossible. So you have to really engineer this kernel function. With their method, they show that after training CNP, the infilling, or the predictions that they're able to make, in this case, the conditional sum of the pixels that try to predict all the rest of the pixels, looks very realistic. Okay. So this is just to show you the relationship between Gaussian processes and, meta learning setup, and how the way the problem is actually set with this multiple tasks and 2 levels of optimization is nothing more than just a hierarchical Bayesian model in kind of general sense, right? Okay, so I'm gonna give you a quick note on the software packages. If you are interested in using meta learning, or you're already using meta learning, one way to start research or to do research is to look into the research code releases, right? And right now these are ubiquitous. Oftentimes a new paper comes with the code. From my own experience, code from code releases is often very fragile. Sometimes it's broken. Sometimes it works. But even if it works, it's a lot of effort to take this code and adapt to your own problem. So the community has started coming up with some libraries and implementations, reference implementations for some of these methods. Those 3 are probably my favorite ones. So actually the first 2 are PyTorch libraries that use that basically implement MAML and MAML-like methods, as well as prototypical networks, and a bunch of kind of few-shot classification problems. So you can go and look them up. You can easily run them and test and benchmark existing methods on these on existing benchmarks. Higher library actually came out a bit later after these 2, and it provides you lower-level building blocks that you can reuse for gradient-based meta learning. So if you're building a meta learning pipeline for something that has not been considered before, let's say maybe for some medical application or something like this, you can use higher primitives within the PyTorch in order to build your pipeline. And I guess I would add a little plug that there is a new library that I've been working on, which is based on TensorFlow. All these previous libraries are based on PyTorch. This one is based on TensorFlow. And the focus of the library is actually to provide building blocks that are a bit higher level than higher, right? And a bit lower level than these pre-built, precompiled, sort of pre-built libraries for existing methods. So they can reuse these building blocks and quickly assemble the meta learning methods that you're interested in trying out. Right. Yeah, so this library is currently under active development. It's very fast and modular, and this is the focus. The focus is on modularity. We're planning to support a lot of things, and I'll be running a tutorial actually next week, so for some friends and collaborators at CMU. So if you're interested in learning more, you drop me an email. Okay. All right, so this sort of concludes the first part of the lecture. Let's just go through a few takeaways. I guess the first takeaway is that there are a lot of real-world scenarios that need something more than just the standard machine learning paradigm with the training and test set and IID everywhere. And perhaps going beyond learning once is a good approach. And meta learning actually does that. It proposes to learn an algorithm, right? So learning to learn, or meta learning, attempts to solve this problem, and it defines this rich multitask setup. And instead of learning a single function, we try to learn a generic kind of meta function that outputs functions for every single task. And so there are 2 families of methods that we consider. Of course, these are not the only methods. There are so many of them, and there are many hybrids, many extensions, many improvements. Like literally every week, you can see maybe 10 to 15 new papers that actually cite MAML, and this is a very fast-growing subfield right now. Again, is it about adaptation or representation? I looked at one of the papers. It looks like it's more about representations than adaptation, but it's very dataset dependent. So exactly the same study with MAML versus ANIL on some other dataset, or maybe even NRL setting, would not work. People haven't done that, and it's still an open question. And something that I did not cover, but I find very interesting, that meta learning can be actually used as a tool or a mechanism for causal discovery. And there's a recent paper from 2019 by Yoshua Benjo and others on how to actually use meta-learning, or this rapid adaptation of different learning rules, in order to discover which mechanisms, potentially, which variables are related to which in a causal way, and which relationships are not supposed to be causal, or not supposed to be present in the model. Okay, so any questions so far before I go to meta-RL? Okay, if there are no questions, let me go to the meta-RL part right now. Okay, so far, I talked about mostly supervised learning applications, but it would be natural, as we will see, to extend many of these methods to reinforcement learning. And so let's go back to our original chart, right, with the standard learning and learning to learn, with our distributions over tasks and distributions over data and the adaptation rule. So while in the standard, or I guess like on the supervised meta learning setup, right, we have this tasks, adaptation rule, and task descriptions. And meta-RL, we can further specify it and narrow it down, where the distribution over tasks is going to be distribution over the environments that the agent gets to interact with. We train a policy update rule instead of just this, arbitrary adaptation rule that can solve new environments, right, given only limited or no initial experience in that environment. And here's just a simple example. Imagine you have a distribution over mazes in which agent can go and try to find the goal, where the goal is this blue square. And the mazes would differ slightly in the topology, and the mazes would differ in the position of the goal, right? So before adaptation, the agent would go and try to explore the maze, and then eventually find it, hit the goal, and stop at the goal. If you go and rerun the agent in the same environment, which means that the same topology and the same goal position, after the adaptation, we would expect the agent to quickly go and directly go to the goal. So this is what happens, and this is just an illustration from one of the papers that looked at this application. But more broadly, the setup is the following. So imagine you have a distribution over environments, and each single environments might differ from each other in the dynamics of the environment. They might differ in the reward function. They might differ. They might be differ in both of these aspects, right? And you have some sort of meta-RL algorithm, right, that produces a fast RL algorithm. And why is it fast? Well, because given a new environment, so say environment X, your fast RL algorithm is able to quickly, interact with this environment. And after just one or a few trajectories, all the consecutive or subsequent trajectories of that fast RL algorithm are going to achieve very high reward. And so this is the basic conceptual diagram that describes meta-RL. Right, but just to give you a quick recap before we go into specific methods such as MAML for RL, let me just quickly recap how do you learn in reinforcement learning, right? And this is a slide from one of my previous lectures where we looked at policy gradient or policy optimization, and eventually we derived, right, this algorithm that consists of 3 steps, where you under some policy, you sample trajectories. Then you construct this objective function, and you compute the gradient of this objective function, and then you go and update parameters. And then you resample trajectories again, and then you repeat, okay? And then to compute the gradient, we had to use this, the log gradient trick. And eventually we got this objective function that you see on the slide. This is not the most optimal objective. There are other objectives that are lower variance than this one, right? But the point is that as long as you have objective, you can literally reduce your reinforcement learning into a kind of data collection loop where you generate samples, and then you sort of roll out the policy, and then you improve the policy and come back and sort of close this loop. So generate samples, compute the objective, compute the gradients, apply them back to the policy. Okay. Right. Now, if you want to do on policy meta-RL, well, we can do MAML again. because MAML is pretty model agnostic. It doesn't really care about what kind of loss you use and what kind of gradient, where the gradients are coming from. As long as you have the loss and as long as you have the gradients, and as long as you have two separate data sets, right, you can do MAML. Right, so in this case, you start with a common policy initialization across all your tasks. We're going to call it theta. Right, given a new task, you're going to go and roll out and get a bunch of experience, right, a bunch of trajectories under this initial policy from this task, right? And then you're going to adapt by computing the gradient of this J function, right? Then you're going to adapt the parameters, maybe with one gradient step, maybe with a few gradient steps, but you'll get this phi I that is suitable for task Ti. Now, to train this whole construction, right, you're going to do the same thing as we do for MAML. We're going to compute this J-test, and know that the J-test is going to be computed on the trajectories that were rolled out using the adapted parameters, right? So you'll have to do two rollouts. First, you roll out trajectories under the initial policy, you compute the update, and then you roll out again under the adapted parameters, or with the adapted policy. Okay, and then after that, you can construct this objective. Everything depends on theta. It's fully differentiable, so you can minimize it with respect to theta. Again, intuition is identical to the intuition we already had with MAML. Right. What we can do further is try to look at it at adaptation as inference in this case. Right. So you can treat the policy parameters, the tasks that we have in the system, and all trajectories as random variables. And we'll see why, this graphical model is important and interesting, right? So in this graphical model, again, we start with initial parameters. We have adapted parameters. Adapted parameters depend on the initially rolled out trajectories as well as the original parameters. And then the final trajectories on which we compute the loss depend on this adapted parameters, and of course the task. Basically, the task here specifies the reward function, if you will. Right. So just to give you an illustration, so first of all, meta learning in this case is equal to learning a prior, as I already said in this hierarchical base model, and adaptation is basically the inference. Right. Now, this is just to illustrate this on one of the reinforcement learning tasks, where the goal is to make this cheetah robot, which is actually a one-dimensional robot, to run in a specified direction, either run backwards or run forwards, right? And after training MAML for a few steps, right, on a lot of environments, and in this case, it's basically different velocities and different directions will specify different tasks, right? This is the initial behavior that you get, right, the initial trajectories, and then after the adaptation, you can get for the backward tasks behavior on the left and for the forward task behavior on the right. Right. Okay, so that was MAML. That was MAML. So that was on-policy RL, right, converted into on-policy meta RL. So the natural question, can we do something similar in the off-policy setting? Right? And there is, originally there wasn't, but right now there is. There are pretty good off-policy meta RL algorithms that are actually extremely sample efficient, as you would expect from the off-policy reinforcement learning algorithms. So how do they work? So I'm going to go through kind of high level through a bunch of basics from this paper called Pearl, the proposes method called Pearl, that appeared at ICML 2019. Right. So again, when you interact with the environment or with different tasks, you technically collect a lot of experience. So in case of MAML, we would interact on policy. We'll collect these experiences, adapt policy, collect again experience, do the optimization step, and then discard everything. Okay, and then go and interact with a new task, do these two steps, and then discard everything. So instead of discarding, how about we just run a policy, collect a bunch of experiences from different tasks, and store them in the replay buffer. Right, then after that, from this replay buffer, we can try to learn, it's called task inference function, in this case called Q-phi, where we try to infer the representation of the task explicitly. So before, we thought the task is represented basically by a bunch of trajectories that you roll out under the initial policy. Right? In this case, we'll try to have an explicit representation computed by this Q function. Okay, and then we can formulate this whole, assuming that we have a lot of data, right, in the replay buffer, we can formulate this as a variational autoencoder problem. Okay, so what I mean by variational autoencoder, you have observations which are coming from your replay buffer, and you have some latent z's. Now you'd like to learn basically the conditional distribution of qz given c, where c is the context or it's coming from the replay buffer. And the objective function that you have here on the slide is basically the kind of generic variational autoencoder objective. We have this DKL between the prior and this posterior, maybe weighted by some data, and so the beta VA. And typically in VAE, you would have here the evidence, right? The log probability. But generally, you can have a different objective function, a slightly different kind of loss function here, and still be a valid VAE. So you can have Wasserstein loss maybe, or something else. So what these, first of all, what these authors propose, first of all, they propose a specific structure for the Q function. They say that the Q function that computes the representation of z given the trajectory is multiplicative, right? So you can decompose trajectory into triplets of overlapping state action state triplets and their work. And by looking at this triplet, you can run them through the same, exactly the same kind of neural network that would compute some sort of representation. And then you would put a Gaussian around this representation, and then you'll multiply all these Gaussians together. So this is the assumption that these authors make. So this makes it easier to compute this DKL objective, and it simplifies the math. So the other cool observation that they make is that we can define this R task Z function that defines the actual loss, or the reconstruction loss basically for the VA. We can swap it and define it through the Q function. Right now, the intuition is that if we have a Q function that also depends, that is conditional on the task, right? If the task representation was inferred correctly, right? If the Z function was good, right? Then the Q function, the conditions on this task should be also good, right? So the Q function also depends on the policy, right? Because usually you say Q theta or Q something, Q pi, corresponds to the respective policy, right? You can have a Q that is not related to any policy. And in this case, you have policy, let's say pi theta, so this Q would be parameters by theta that corresponds also to the parameters of the policy pi theta. So basically you connected your variational objective through this L critic, this function, with the objective that actually makes sense from the reinforcement learning perspective, right? So you'd like to find the Z such that your Q function actually can distinguish well between the tasks, and this Bellman error, or the TD error, one-step error that we covered in one of the previous lectures, is actually minimized. Similarly, you can define a loss, or the actor loss for the policy, and alternate between optimizing the policy, right, and optimizing the inference function. And if you use the soft actor critic, right, soft actor critic approach, or the soft Q learning approach, these two functions, Q and pi, will be actually coupled, right? So you can, as I showed in one of the previous lectures, they're basically mathematically related to each other. So you will essentially be alternating between optimizing these two objective functions with respect to theta, which parameterizes Q and pi, right? And phi, which is parameters of the inference network, the task inference network. So the key points that these authors make, right, is that first of all, you can infer explicit latent representations of the trajectories. You don't need to sort of hide everything on this kind of MAML style gradient adaptation, right? Second of all, you can decouple parameters of the inference network. One second. Decouple parameters of the inference network and the parameters of the policy and the Q function, and alternate between the two, which allows you to kind of train them in tandem, but also allows you to use this off-policy data collected while training the whole the whole pipeline. And finally, all objectives in this case involve both the inference network and the policy network, or the Q network. So if you look at both of these objectives, they all depend on theta parameters and the phi parameters, and your algorithm is going to be basically iteratively optimizing the two. So you're going to alternate between optimizing these parameters, optimizing phis and optimizing thetas, as well as collecting more and more experience as you see needed. Right? There was a question somewhere.
Right. I had a question about what makes this off policy. So is it because the Q is a multiplicative posterior distribution, is that the only reason that this can be made off policy? Because the order of the transitions is not relevant here.
That's right. That's right. Yeah. So the multiplicativity actually makes it suitable for off policy, so that the Q function actually does not depend on the entire trajectory, but only on just a single sample. Technically, I see a way to extend it to multiple transitions. Like if you really want to use like truncated backpropagation with a recurrent neural net, you can still apply it. And instead of storing triplets in your replay buffer, you can store entire trajectories. So to fit the Q function, right, you'll still use triplets because you have the TD error, and you don't need anything more than just triplets. But let's say to fit the inference network, you would use the entire trajectory. How well that would work, I'm not sure, but it seems to me that you still should be able to keep reusing your replay buffer. Does that answer the question?
Yes, thanks.
Okay. Yeah, so this method, why it is so interesting is because the results turned out to be remarkably good, right? You can look at MAML that I just described. There's this other RL squared method that we didn't go through in ProMP, which is kind of sort of MAML plus, if you will, with a lot of corrections and improvements to how these like second order gradients are propagated through the objective. And this is Perl, right? So if you look at the curves, so literally Perl already outperforms the best methods somewhere, after just 1 million steps on these simple environments, while the MAML or other adaptation-based methods are just starting to take off. So similarly, for the half cheetah velocity, it already solves the task literally at almost, let's say, 1 million steps again, while MAML is going to take a few, hundreds of millions of steps to get to that level. All right, so this is really interesting because it's much more sample efficient. On the other hand, you can ask a question, and I guess the relationship between Perl and MAML for meta-RL and MAML and protonets for supervised learning is sort of similar, right? Here you learn explicit representations of the tasks, right, as sort of embeddings in this latent space, and with prototypical networks, you basically do the same, right? You learn this prototypes of representations of the classes, and again, if you run prototypical networks and MAML on the supervised learning setup head-to-head, you would see that prototypical networks literally achieve their and saturate within maybe a few hundreds, maybe 1,000 steps, while MAML takes a few thousand steps. Right? So there is an order of magnitude difference in terms of efficiency, and it turns out that explicitly learning representations could be more efficient. But also you can go one more step and ask the question: how much of this like entire construction that are sort of meta learning driven, right, where you decompose your tasks into different tasks, and do you actually need to decompose tasks into different tasks, have some initial experience and then optimize on the final experience, right, on the test trajectories? So basically sample from task training trajectories, optimize the whole system on the test trajectories. And the answer is probably no. There is a paper called meta Q learning that actually shows that if you take the standard Q learning and just add the standard inference function, which is going to be a recurrent inference function, and try to condition your Q function on the representations inferred by the inference function without all these fancy kind of combinations, you can still perform as well, almost as well as Perl on many of these benchmarks. Okay. All right, so I'm gonna slightly shift the gears from here, since we consider both on-policy and off-policy meta-RL. I'm gonna look into the problem of non-stationarity, the problem of non-stationary environments. And the question that we can ask, so this is great. We have a lot of tasks. Now we have a distribution over all these tasks. We assume that these tasks are coming to us IID somewhere. Right, given a new task, we can observe a few samples from this task, maybe try to interact with it, and we're going to solve it. Okay. Now, the adaptation of this case is literally as shown with arrows, on the right-hand side, right? We have to like tasks are sort of independent and fully decoupled, and the fact that we're able to meta learn something and then sort of perform well on the new tasks is coming from the fact that these tasks are somehow related, and this is captured by the shared representations that we learn on the meta training set. All right, but what if we are in an stationary environment? So let's say we have a single environment, and then task somehow drifts over time, right? And then we don't know exactly how it drifts. Maybe it drifts consistently. It makes sense to assume that whatever is happening to the next task, let's say to task 2 and task 1, they could be related. Task 3 and task 2 would be related. Task 4 and task 3 are somehow related, but maybe not. We don't know exactly how they're related. Can we still use meta learning to sort of approach the problem of non-stationarity somehow? Right, and I'll give you just a simple example of how what a non-stationary environment can look like. And in this case, it's an example from a competitive multi-agent game. So let's say you have an agent and opponent, and the goal is to adapt to a learning opponent. So it means that the agent initially faces an opponent, and maybe the opponent initially is easy. It's the opponent's competence is not that high. You know, the opponent will improve over time, right? The opponent is going to learn by interacting with the agent, and you know, in the round 2, the opponent will actually be more competent, right? And then the game can go on, and round 3, 4, etc. The opponent's competence can change and improve, and therefore, from the agent's perspective, the environment that it gets to interact with in every single episode, right, every single round is going to change. And so each new round can be seen as a new task, and we can think of this non-stationarity from round to round as a sequence of tasks, right? So how can we go and solve this problem? Well, so first of all, from the modeling perspective, right, again, all these tasks become dependent, and what we would like to do, we'd like to learn an adaptation rule, not just within the task, but the adaptation rule that can jump from one task to the other, okay? And then to actually design an algorithm that is able to solve this problem, you know, we need to, you know, sort of meta learn to exploit these dependencies, right? So how do we do that? Well, first of all, let's just start from the, you know, graphical model that I just introduced. And I said it's going to be handy for us to use it later because, you know, the beauty of graphical models is that you can put all the variables kind of on the canvas or on the slide, on the whiteboard, and reason about what are the variables in the system. In this case, we have a single task, or, you know, sort of independent task, right, and a bunch of dependent variables such as trajectories and sort of the parameters of the policies or parameters of the Q function. Right? In case of this continuum of tasks or continuously changing tasks, right, where we would like to continuously adapt and hop from one task to the other to the next, the new variables that we have in the system are going to be new tasks. So at every instant in time, we are no longer interacting with the same task, right? We're going to be interacting with new tasks, and all these tasks are going to be sequentially dependent. Okay, so every time that we start, let's say we start with some initial parameters, we're going to interact with the first task, but then the parameters for the next task, right, we'll have to produce trajectories that are actually in a slightly, you know, are coming from let's say a different opponent or from a different situation that drifted from the original one. And our goal right now is to learn from a graphical model perspective. Our original goal was to learn this adaptation function here, right? Now our goal is simply to learn an adaptation function that hops from phi0 to phi1 to phi2, etc. And given a graphical model fully specified, we can technically write down, you know, hierarchical base model and generic inference function, and then try to approximate it. There was a question. Oh, there's a question in chat. Okay.
Yeah, I was asking if you also considered catastrophic forgetting during the adaptation.
Right. So in this setup, yeah.
Yeah.
So catastrophic forgetting, just to define it, is actually relevant to the case where you'd like to learn as many tasks as possible and also retain knowledge about these tasks, right? In this case, in the case of continuous adaptation, you technically, so the setup is such that you don't really care about catastrophic forgetting because your tasks are going to be changing from T0 to T1 to T2, etc., until infinity. So assume that there is some sort of Markovian dynamics. Yeah. So you'll never just go and try to solve arbitrary tasks in this sequence. You care about catastrophic forgetting where someone externally wants your agent to, you know, different tasks and want to solve them. And there is no way to control how, this person or someone points you to these tasks.
Okay. Also, do you see any kind of curriculum learning in this, or was it like random task one after another?
Yeah. So in this case, so we're going to come to the applications, but we did indeed we considered curriculum learning. So we always started from simpler tasks so that you can learn them quickly, and then the next task is going to be a bit more complex, and the next task is going to be a bit more complex. So if you look actually at this example that I just gave with robots, right? It's a sort of natural curriculum where your opponent is learning, opponent is changing, the competence of the opponent keeps improving, and you're trying to train your agent to face increasingly more competent opponent.
Okay.
But yeah, I agree that curriculum is going to be basically something that really defines these transitions between the tasks. And one research problem to consider is actually to try to design better curricula that would enable more efficient meta learning.
Yeah, thank you.
Okay, so from we can technically, as I said, like given this graphical model, we have the full information to go and design an algorithm, and the simplest algorithm that we can come up with is based on MAML, where we simply just change the objective function, right? So we alter the objective function that accounts for this pairwise dependence between tasks, right? And instead of trying to roll out the first trajectory from one task and then to adapt the policy to another task that performs, to adapt the policies so that it does well on the same task, now you try to roll out trajectory on one task and then adapt the policy such that it's gonna do well on the subsequent task. So at training time, you can do that, and assuming that this Markovian dynamics between the tasks does not change from train to test, then technically, as long as you're able to adapt to this non-stationarity at training time, the type of non-stationarity is going to be similar at test time. So you should be able to adapt to it as well. All right, so just to give you a quick example in the last few minutes, the environment that we designed for this was RoboSumo. All right, so it's a competitive multi-agent environment where the goal of the agents is to compete against an opponent, and the opponent's behavior is going to change over time, just exactly as I told you, right? So it's going to be multiple rounds in the game, and the opponent's competence is going to be improving from game. Each round is multiple episodes, so your agent is going to interact with the opponent, and then after it interacts with the opponent for a little bit, it has to adapt, right? Knowing that the opponent is going to change as well. And this is probably the most kind of interesting evaluation that we conducted in the setting. So we had a large population of the agents of different anatomies using different policies and using different adaptation strategies, and we tried to test which of the agents will eventually outperform the other agents. Right, so we started running a lot of games. We would subsample 1,000 pairs of agents from the population. We would run a bunch of games. Right, and whoever wins from the game, right, wins the sequences of rounds within a single game, is going to get replicated, and whoever loses gets removed from the population. So over time, you can see how the meta learning methods, right, certain policy plus meta learning, in this case LSTM policy plus meta updates, tends to entirely outperform all of the agents and sort of overtake the entire population. You can also see that the morphology of the agents, right, or the anatomy of the agents, such as like 3-leg, 6-leg, 2-leg agents, also plays a role. In this case, 6-leg agents turned out to be one of the most sort of competent in this scenario. All right, so we're at the end of this lecture, and just a few takeaways for you for this part of the lecture, right? So the meta learning setup seems to be very, very suitable for reinforcement learning, or in general for sequential decision scenario, whether it is imitation learning or whether it is reinforcement learning formulation. In either case, collecting a lot of experiences is hard, right? Or interacting with different environments for a long time is hard. You know that in reinforcement learning, you need like millions of steps in order to master a task, and it's sort of meta learning really tries to bridge this gap and to sort of reduce this number of the requirement of the number, either demonstrations or number of samples or interactions with the task. We'll look at the on-policy and off-policy meta-RL algorithms, right? We see that both on-policy and off-policy can be sort of upgraded to the meta-RL setup pretty easily. We can decouple task and inference, and then there's still this question of about fast adaptation, whether it's about adaptation or whether it's about learning representation. What we did not discuss is exploration in meta, and especially in reinforcement learning. Exploration is an important question. All the examples that I showed you used denser words, so exploration is technically sort of circumvented by reward design. But you can also see a discussion in meta-Q learning that I mentioned, where they argue that actual representation matters more than the adaptation. And finally, probabilistic view of meta-learning that we looked at in the first part of the lecture and in this part of the lecture is kind of important because it allows you to use meta-learning, extend meta-learning ideas from this distribution of tasks to more, beyond simple distribution of tasks, maybe to chains or other sort of scenarios where tasks are dependent with each other. And by just getting this graphical model, you can naturally derive the algorithm for solving it, and it's going to be a new algorithm for basically meta-learning and adaptation. And so it's a very active area of research. So there are so many papers that coming out literally every conference. So it's very, very, very exciting, and it's also very hard to keep track. Okay, any questions so far? I think it's end of the time. I'm a little bit over time.
Yeah, I had a question.
Mm-hmm.
Because MAML does truncated optimization, so how much adaptation do you think we can do in the updates? Is it even possible to adapt properly?
Right. This is a good question. So in simple environments, in my opinion, it is reasonable to adapt. There are two aspects to it. So one of them is how good these gradients are, like how informative they are. And how informative they are actually depends on how noisy the data is, right? How much variance you get by looking at a specific objective on a specific kind of batch of trajectories. So for instance, with this continuous adaptation, we had to use like enormous batches to get any signal out of MAML. The other question is like how far the parameters actually travel, right? How much you need to adapt. And if you look at the Anil paper, right, you actually don't need to adapt much. You really need to adapt like some very small number of parameters a little bit to get a different behavior or like a different classifier. So you observe the same thing. You have to meta train the model for a long time.
But is adaptation that a problem of our benchmarks, or is it like it's only possible with such simple benchmarks and it won't work for like in some scenario where there are more difficult settings, like two relatively different like data sets that we want to adapt on from the same training set?
Sorry, so your question is whether MAML works only on specific data sets and then it wouldn't work for some reason on other data sets?
Like why Anil is able to work is because are the benchmarks simple, or like do we need to improve those, or it's only able to work on these and we cannot?
Yeah, this is a really good question. So I don't have an answer. So they analyzed Anil and like they did this analysis of MAML and Anil only on Omniglot and Mini ImageNet. If you look at recent papers in meta learning on, few-shot classification kind of branch of meta learning, you see that there are a lot of baselines that are coming out right now that literally don't use any meta learning. So it's basically train a function on all these kind of tasks, right? And then do some post-processing, and then voila, I get like a good enough model that generalizes to test tasks. So I think it is the problem with the benchmark. It is the problem with the benchmark, and a lot of researchers in the field actually argue for better benchmarks and more kind of diverse task distributions. There are a few papers that look into that. In meta-RL specifically, to go back to your question with like this multiple MAML steps, technically you could do, more kind of steps within the inner loop, and there are papers that allow you to almost converge until the, go until the local optimum.
Yeah.
I haven't seen them applied to meta-RL, but I've seen them applied pretty successfully to few-shot classification.
Oh, okay.
So yeah, I guess like MetaRL, one of the downsides as a test bed for meta learning could be, so it's great for solving a task if you have a specific robotics task, right? But as a test bed, it's a little bit hard to disentangle where the contributions and the problems are coming from. Is it from, noise of the problem, or is it from the fact that there's something wrong with the gradients, we don't take enough gradients, or is it, where is the contribution coming from, the representation or from the adaptation itself? So ideally, we'd want to have a really nice suite of benchmarks that we can say, oh, this benchmark actually tests representations, and this benchmark tests adaptation. And this one actually requires more than case steps of adaptation just by design. So that would be fantastic, but we don't have it right now.
Okay. Thank you.
Sure. Any other questions?